Okay, this lesson is on DC machines. So first of all, I would like to mention that a machine can work as a motor or as a generator. When a machine works as a motor, so it converts electrical energy to mechanical energy. So on its input side, it takes in electrical power, and on its output, it produces mechanical work. At the same time, when that machine is working as a generator, it takes in the mechanical energy and produces electrical power, electrical energy. And most electrical machines can be used, it's the same machine, so no change in the construction, can be used either as a generator or as a motor. So now we're going to come to, so that was the idea about motor and generator. Now since this chapter is about DC machines, so there, when we're saying the motor takes electrical energy, so here it's going to be DC power. And when we're saying produces electrical energy, so here it's going to be again DC electrical power. So when I'm saying DC electrical power, so if we look at a graph on the side, so if this is the voltage or the current graph with respect to time, so DC has a constant value with respect to time. Instead, if it was AC, so the most commonly used form of AC, again voltage or the current on the y-axis, comma I, and the most commonly used form is the sinusoidal variation. So voltage or the current, when it's AC in nature, alternating, it has a sinusoidal variation with respect to time. All at the same time, for DC, it has a constant amplitude throughout. So not a function of time, does not change with respect to time. So we're clear here, it's the DC power, here it's the DC power, that's what makes the DC machines. And we looked at the generator or the motor side. Now the electrical motors are used in a very large number of applications. Like you can think about a refrigerator, it uses an electrical motor. You can look at the washing machines, the fans, the power windows on your cars, the wipers on your cars, elevators, many applications. So these are the small applications. You can also look at some industrial applications where there are larger electrical machines used with more power handling capabilities. So industrial applications, you can look at rock crushers, compressors, so those kind of application, pumps, so those are some kind of industrial applications where you can see the use of the electrical motors. So electrical motors are used a lot. Okay, so, and you can also see that either it works as a generator or a motor, it's rotating machinery. It's rotating. So before we go into the actual operation of a rotating DC motor or rotating DC generator, we're going to look through the operation we're going to look through the operation of a linear DC machine, the one which does not go in a rotational motion, the one which goes in a linear motion. So linear DC machine. So we are considering here, what is the machine? Which part is actually the machine in here? The part which is the machine is this section. So this is your machine. This element in here is your machine. Okay. And for the time being, its name is not a DC machine, its name is a conducting bar. And how we have this set up in here, you have a conducting bar that is stationary to begin with. You have a magnetic field existing in here. This magnetic field is present from an external source to produce that magnetic field. It could be a permanent magnet, it could be another electromagnet which has produced this field. Okay, and the presence of that field, B in here, is shown by these crosses in here, which shows the direction of the magnetic field. So if you look at B, the direction of the magnetic field, we're going to consider here that it is into the page. So this magnetic field is existing. Now you have a conducting bar present inside the magnetic field. So what we're going to do now, we're going to supply somehow, we're going to make the current flow through the conducting bar. How are we going to do that? So to begin with, we have some other parts in this experiment. So those parts are, we have a source of electrical power. So that's the source of the electrical power, VA. That's an external source. And then there are conducting rails in here. So this is a part of the conducting rails. Or maybe this one will be better. So that's the part of the conducting rails. And these conducting rails do not offer any resistance. So the conducting bar can move freely on those conducting rails if there is any force into the picture. So at the beginning, the conducting bar is stationary. Now, when we close the switch, so before we close the switch, where is the switch? This is the switch. Before we closed this switch, the conducting bar is stationary. Even when we just close the switch at t equals to 0, even we just close the switch at t equals to 0, the bar is stationary. So few assumptions, it's an ideal machine. The rails, the conducting rails and the bar have 0 resistance and there's no friction. So as soon as we close the switch at t equals to 0, so the switch will be closed and this is how the situation will look like. Okay, and what we expect, the current flow starts here. So the flow of the current starts here from the positive side of the source through the resistance, through the switch, through this conducting bar downwards and back to the left and to the negative side of the battery. So that's the complete path of current. So when you look at this current flowing through the conducting bar, it's flowing from top to bottom. So you follow this. So here I try to draw. This is the current flowing through the conducting bar. So this is the direction of the current actually right now, if you see, and we're labeling them IA. Right when we just closed the switch, the current value is given by the total voltage divided by the total resistance in the system, Ohm's law, in clockwise direction. And that current IA at time t equals to 0 plus. So this is just the time right after when the switch is closed. So the total voltage in the system is VA, the total resistance in the system is RA. So using Ohm's law, I is given by VA divided by RA. So that is the initial current flowing in this system right after we close the switch. Now, so now you have a current carrying bar. So now this bar is not only just the conducting bar, it's a current carrying bar. There's a current flowing through the bar, IA. A current carrying bar is placed inside the magnetic field. Once you have a current carrying conductor placed inside the magnetic field, it will experience force. And that force amplitude is given by, the force amplitude is given by I, the current flowing through the bar, IA, the length of the bar, so that's the length of the bar. Here you can see. So that's the length of the bar inside the magnetic field. multiplied by the magnetic field strength B. And the direction of this force and the motion that force is going to cause to the conducting bar is given by Fleming's left-hand rule. Now, with Fleming's left-hand rule, it's your left hand. The first finger is the direction of the field. So the direction of the field is into the page. The second finger is the direction of the current. So this is your second finger, direction of the current, right? Because IA flows from top to bottom through the conducting bar. First finger into the page, second finger top to bottom, and now you will see that your thumb, which is the direction of the force, is pointing towards right. So this is the direction of the force present. That's your thumb. So that's your thumb, which is pointing towards right. This is your second finger on your left hand. So thumb points towards right, so that means that's the direction of the force, which is given by IA L times B. So that means the bar will start moving towards right. This force that will cause the bar to start moving towards right. All right, now the bar gains some speed, some velocity V, and as it cuts through the magnetic field, now you have a moving conductor inside a magnetic field. So according to Faraday's law of electromagnetic induction, or when you have it here, you don't have actually the changing magnetic field, but even inside the constant magnetic field, once you have a moving current carrying conductor, a voltage is induced across the two ends of the conductor or the bar. Now, the voltage induced is given by, in terms of its amplitude, it's given by E equals to BLV. So again, B is the magnetic field strength, L is the length of the conducting bar inside the magnetic field, V is the velocity it's going at. In order to understand the polarity, because we're going to have a conductor like this, right? We are having a conductor like this, conducting bar like this. So we're going to see if the voltage is induced across it, let's say E, will its top end will be positive or its bottom end will be positive. So in order to know the polarity of the induced voltage, we're going to use the right hand rule now. So this is the right hand rule. So the first finger is the direction of the field, which is into the page. The thumb gives the direction of the motion. So this is the thumb, right? That's your thumb. Towards the right, velocity. Okay. So with your right hand, first finger, the direction of the field into the page, the thumb towards the right, and you're going to find that your second finger is pointing like this. So here is the palm of your hand. So this end positive and that end negative. So the polarity of the induced voltage will be like this across the bar. Okay. Now we can draw this system, this machine, using an equivalent electrical circuit. So here, the part of the equivalent circuit will all be the electrical components. So that's the electrical components. You have a battery in there. That's the electrical circuit component. You have the resistance in there. There's a switch which is controlling the flow of the electrical current. And now the conducting bar, you can see in order to represent it using an electrical component, it's the source of the voltage because there is induced voltage across it. And since we have assumed it as an ideal machine, so there's no loss, there's no internal resistance that it has. So you can see how the two ends, you can relate the polarity in here. So it's the same polarity, top end positive, bottom negative, and that's the source of the voltage E, induced voltage, and its value is given by BL times V. And you can see as you look across, you can see that the induced voltage E is in opposition to the source voltage VA. Now, since E equals to BLV and you saw that the bar is actually gaining velocity. As this velocity goes up, the value of the E goes up as well. Okay, so the value of the E goes up as well. So the energy is absorbed by the induced voltage And this energy shows up as the kinetic energy of the bar. The bar speed eventually becomes high enough that this value of E will become equals to V. So now this E is going up, the induced voltage at one time. Once it's going to have enough value for that, this will be good enough to be equals to VA. And at that time, once E equals to VA, the IA will go to 0. And once that current goes to 0, there will not be any force which depends on IA. And the bar will keep coasting at that constant velocity, but its velocity will not go further up. So you can see in this circuit, if you close the switch, you're going to apply KVL, and that KVL gives you negative VA plus RAIA plus E equals to 0. And this equation can be simplified into here. So IA equals to VA minus E over RA. And you can relate here as well as soon as E goes up to the value of VA. So as soon as they both are equal, the current goes to 0 and there's no further force build up. So what will happen is the bar will keep coasting since there's no friction, there's no, we're assuming it as an ideal machine. So the bar will keep on coasting at a velocity at which E becomes equals to VA, but there will not be any further increase in the force or further increase in the speed of the bar. Okay, now we're going to look at the operation of this system as a motor. Okay, so what happens in case of a motor? So here was the bar. We're assuming that there's an external force available. We call that mechanical load. There's some external application. So load is an application, mechanical application. That is exerting a force to the left. So on this bar, there's something which is exerting a force on this, and we're going to call that as the applied force, okay? You can call it as load force as well, because that's applied by the external load. Now, as soon as this force is applied, yeah, but keep the volume a little low, okay? Sorry. So, okay, we're saying as soon as this force is applied, so since the bar was moving towards the right, like this, so this force is in opposite direction to its motion, so that will slow down the bar. So as soon as it will slow down the bar, so that means the velocity will go low and the E, the induced voltage, will go low as well. Now, what happens with that? You also know EIA equals to VA minus E over RA. VA is constant, RA is constant, so as E will go low, this IA will go up. As this IA will go up, your force, which is directly proportional to IA. Now, what is this force? This is the force which is produced by this system on the bar. Okay, it's not the applied force, it is the induced force. Okay, this is the induced force from the machine. So this force will go up with the current going up. The force exerted on the conducting bar from the magnetic field, which is towards the right, will go up. So then what will happen is, at one time the velocity is going low. Keep in mind the velocity of the bar is going low. So at one time the bar will just be at a certain velocity V, lower than its original value from where we have started. The bar will be running, moving at a velocity, at a lower velocity, at which the force created by the magnetic field, the induced force, equals to the load force or the applied force. Then what are we looking at? So once that happens, since there's no more external force present there, now it's counteracted by the field, the force produced by the magnetic field. So now the bar will again run at a velocity, but now this new velocity will be less than where we have originally started from. So what do you observe? what you observe, this is where is the element which is taking power. This is where the element which is consuming power. This is where the element which is providing power. This element is providing power. So that's why we call it, this is the power input into the system. And in case by the basic definition of the power, it's given by the voltage multiplied by the current. So the input power at the battery or at the source is given by the voltage VA multiplied by the current IA. The loss in the resistor, now power can also be like V times using Ohm's law, V over R, V square over R, or power can also be IR times I, which is going to give you I square R, okay? So that's what we are using here, since we know although you can use any of these expressions, but since we know the current and the resistance, so we're saying for the resistor, we're going to say the power consumed by the resistor, because for the resistor, it cannot keep that power. It cannot, it's not the useful power. It just dissipates the power consumed by itself as heat. So that's why we call it power loss instead. So I square R. Okay, similarly, the power consumed at this end and here by the conducting bar is given by the voltage E multiplied by the current IA. But this is the power given to the conducting bar. So that's the source in here. That's the consuming element. That's the power consuming element as well. So the power delivered by the source VA, that's converted partly to the heat in the resistance and partly to the mechanical power. So the power P equals to E times IA. That's the developed power inside the machine. So that's the power output from the machine, which is used to take care of the mechanical load. And this will be shown up as the mechanical power. So that's the operation as a motor. Now comes the operation as a generator. So here, the first assumption, of course, we are assuming that this bar is moving at a velocity V. So V is the starting velocity, okay? And then what happened is, from some external source, there's a force applied. And that force applied is in this direction now. Okay? So the direction of the machine moving is also in the same direction. So I'm going to say this is my applied force. And it could be load force as well. So some external means has applied a force in this direction. Now, once you're going to find that since the applied force is in the same direction of the motion, so V will go up instead. Okay, so V will go up. So as soon as that V will go up, this E will go up as well, because E equals to BLV. So now, as soon as this E will go up, because we have started from the starting point. So at the starting point, when this force has just started, E was equals to VA, right? That's why the bar was moving at a constant velocity V. So now, external force is applied, the velocity goes up, E goes up, and E becomes larger than VA. Once that E becomes larger than VA, then what happens? Now we learned that IA equals to VA minus E over RA. Once this E goes higher than VA, so this IA will be negative. So if positive IA was in clockwise direction, the negative IA will be in counterclockwise direction. So this will be the direction of the current. Make sense, guys? So with that direction of current, now what is happening? The current is leaving the positive side in here, and the current is entering the negative side in here. So this is your source of power now. So that's your input power. And the value is, of course, E times IA. That's the source of the power. And this element is consuming, and this element is also consuming. Here it's through the resistor, so heat loss, and here it's actually your output power now. And you can see the input is the mechanical power, which is the force applied by the external load or an external application. And the output in this case is the electrical power. So to the battery, the power supplied to the battery, and battery is an electrical element. So that's the operation as a generator you have. Okay, so now we're going to be looking into the operation of, or into the system of a rotating DC machine, motor mainly. So a DC electrical motor has two parts, mainly two parts. One is the stationary part called a stator. The second is the rotating part is called a rotor. And rotor sometimes called armature as well, especially in DC motor or DC generator, armature. So rotor is the rotating part that's connected to a shaft that couples the machine to its mechanical load. The shaft and the rotor are supported by the bearings so that they can rotate freely. So here is a picture which explains the parts. So you can see the outside this frame, and here is what we term as the stator, right? And then this part is your rotor, which is, you can see that this is the shaft in here. Okay, and that the shaft or the rotor using the bearings is placed inside the stator or the frame so that it can run properly, it can rotate properly without having all its part flown away. So rotor, armature is the rotating part of the machine, and stator is the stationary part of the machine. So more details you can see. So we have a bit of explanation added to the stator. So stator consists of a frame or a yoke. So that's the frame, or its name is also called the yoke. Okay. Yoke. All this is yoke. So that's the parts of the yoke or the frame. And the pole pieces, which project inwards and provides a path for the magnetic flux. Where is the pole pieces? So this is where the pole pieces are. That's your pole pieces. So you can see there is a more spread where it connects where it's there to the rotor. So that's the spread so that the magnetic field is distributed evenly over the rotor surface. All right. This is called the air gap. Which is the air gap? This is the air gap. That's your air gap. Air gap in here. Pole. And then, okay, so the air gap is done. Okay, now is the windings. So there is a field winding which is used to produce the magnetic field. And where is that winding? This is where the field winding is. This is the field winding. Okay. So this is field winding, which is used to produce the magnetic field. Magnetic field. So we were at the field winding, and I also want to show with the same thing. So here is the field winding that produces the magnetic field. Now we're going to place the conductors or another winding inside that magnetic field so that we can have EMF induced or the voltage induced in there. So that's going to be your armature winding. So the other winding on the DC machine is the armature winding, okay? And where is that? So here is the armature winding or the conductors, and I want to remind you guys, so winding is just another name for a coil. And where those are, it's right in here. Okay, and they are on the rotor or the armature. And where is the rotor? So this is where the rotor is. And which part is the rotor? So the rotor is the structure on which armature winding is placed. And where is the rotor? Rotor is here. So this section is your rotor. So field is produced by the field winding, and that field produced by the field winding is shown in here. So these are the field lines, the direction of B. Okay, so here are the field lines shown just under the poles. Okay, and after coming from here, it takes its path through the yoke and combines back in there. Since you have two sections of the yoke, above and below, so the other section also completes the path. If the total flux is phi, so since it's the same structure above and below, so half of the flux goes through the top part and half of the flux goes through the bottom part and combines back into the phi. One small middle thing in here at the center, so that's the shaft. That's your shaft. Okay, so the armature windings are located on the rotor or the armature. And yeah, that's it. So those are all the parts explained one more time, and the stator is explained in details. So the current in the field winding is independent of the mechanical load. So the current to the field winding is supplied from an external source, and it has nothing to do with what is the load on the shaft of the machine. So field current is independent of the load. At the same time, the armature current, the current which flows through the armature binding, that depends on the mechanical load, and it's directly proportional. So larger the load, larger will be the value of the armature current. Smaller the load, smaller will be the value of the armature current flowing. So when the machine is working as a generator, the electrical output is taken from the armature or the rotor. Okay, so the rotor or the armature consists of a shaft, which is machined from a steel bar with a core built up over it. The core is composed of many laminations in order to reduce the eddy current losses, and has notches along its outer surface to hold the armature winding. The commutator is built onto the shaft of the rotor at one end of the core, and the purpose of the commutator is to convert alternating induced voltage into unidirectional or one direction or constant or DC voltage. So that's the detailed view of the armature, and you can see how these are the notches. Let's use this instead and erase. So these are the notches around the surface in which armature conductors are placed, and they makes the armature winding. And then you can see here is the shaft, okay, and around the shaft you have commutator bars in here, okay, and the brush is used to make electrical contact. Okay, so DC machine, about its basic operation. First, what we're going to do is we're going to relate the linear velocity to angular speed or angular velocity. So V is the linear velocity in meters per second, and omega, now since it's the rotational motion, so omega is the rotational speed, angular velocity, and it's measured in radians per second. Okay, and in radians per second. So we are thinking about an object in here which is rotating on the circumference of this circle with radius r. Okay, let's say the current position of that object is here, which is at an angle of theta, and you know that this total angle is 2 pi. So at theta position, right? So the distance covered at the circumference S is given by r times theta. R is the radius, theta is the angle through which it has rotated. So angular speed by definition is in radians per second, so that's the angle theta divided by the time t in seconds. And then you substitute for theta as S over r, so that's substituted. So S over R times T, and from there you can take S over T separate as a distance over time, which is the velocity, linear velocity, meters per second. So V over R, and V equals to R times omega. So this is the equation which will be used to convert linear velocity into angular velocity, or to relate the angular velocity to linear velocity. Okay, so you can see how the field winding, now the field winding is not only shown in the form of cross or dots, it is actually shown. So this is the field winding. And it's connected in here to the other side pole. So that means it's connected in series. Okay. And the direction of the current is given by this source in here. So that's the direction of the current. So gonna come from the bottom and comes up, down in here, comes down in here. So that is where it flows, comes up from the bottom and comes down from the top, and there it is. So that's the direction of the current flowing through the field winding. And that current flowing through the field winding, you can try to use the right hand rule. What is the right hand rule? So this is the coil, so curl the fingers in the direction of the current, and your thumb points in the direction of the magnetic field. That is how it is, right? So the direction of the magnetic field is there, and so magnetic field is produced by the field winding. One more thing which we're going to pay attention to in here, so the pole area under the pole, the coverage of the circle under the pole is given by these lines. So under the pole, so this is the under the pole, same as on the other side, is limited to minus delta to delta. So this is the angle 2 delta. Okay, so outside of this range, and the same on the other side, so this is also 2 delta. So outside of this range, there's no field in here. That is what we are assuming in this case. Field is 0. So B is 0, let's say. Same as for this side. B is 0 for between outside of that 2 delta limit. Okay, so in order to understand the basic operation, so let's consider a two-pole machine. Two-pole machine, so only north and south. So it doesn't matter which side you place the north and the south. The only idea is that you should label the direction correct from north to south inside the magnetic field. So two-pole machine, and with one armature coil only. So although on the armature you're going to see many of them, and you saw that there were many of them placed them like this too earlier, right? So they were placed like this. Now we're only assuming that there's only one armature coil. So one turn of a coil has 2 conductors. That's always true. One turn of a coil has 2 conductors. So this is one turn to label in terms of the diagram. So this is complete one turn. This part in here. One turn. And you can see the 2 conductors. So one conductor is from here to here. The other conductor is from here to here. So 2 conductors. Okay. So the direction of the magnetic field, and these are the commutator segments. So these are shown as the commutator segments. And the brushes in here. So these are the brushes to make external contact. So this is where you're going to connect it to external connections if it's working as a generator. So this is where the voltage will be induced at, produced at. Okay. So we're going to understand right now how is the voltage induced if this coil, this 2-conductor turn of a coil is rotating inside the magnetic field. So where is the magnetic field? This is where the magnetic field is. So magnetic field is present from the north and the south poles. If this loop is rotating, and it's rotating in what direction? It's rotating in this direction, counterclockwise direction. So that means this side will go up out of the page, this side will go down. That means into the page. So out of the page and into the page, not up and down, sorry. So out of the page, the right-hand side conductor, and into the page, the left-hand side conductor. If it's rotating inside the magnetic field, there will be voltage induced. So the voltage induced for this side, once it goes through the right-hand side air gap, using Fleming's right-hand rule again. So the first finger is the direction of the field. So that's your first finger, direction of the field. The thumb is the velocity which is out of the page, so it's the right hand, thumb is the velocity, which is out of the page, and you're going to see your second finger pointing like this. So your second finger, so let me just write, that's the first finger. Okay, first finger, B, direction of B. And the second finger is going to point like this. So that's going to be the palm of your hand, plus and minus. Similarly, on the other side, the left hand side, for the C to D part, again it's the Fleming's right hand. So first finger B from right to left, and the thumb is the velocity, which is into the page now, and you're gonna see that your second finger now is pointing like this. Okay, so that's only explained about how the voltage is induced in the two conductors. So A to B to C to D makes one turn of the coil. Okay. All right, the ends of the coil are attached to the two-segment commutator, as I said. So here is again the commutator. The ends of the coil is attached to the two-segment commutator. Here are the ends of the coil, which is mounted on the shaft. The segments are insulated from one another and from the shaft as well. The brushes mounted on the shaft make electrical contact. So those are the brushes, which is not insulated, which is making electrical contact with the commutator. Sorry, brushes mounted on the shaft make electrical contact with the commutator segments. So otherwise, the commutator segments are insulated from one another and from the shaft. Okay, now when the conductor passes through the right-hand side air gap, so that's the right-hand side air gap. When the conductor passes through in here and cuts through the magnetic flux density lines or cuts through the field lines, the voltage is induced. So voltage induced between the points A and B is given by, of course, BLV according to the voltage induced expression, and the V now is going to be changed to angular velocity, so BLR times omega. So voltage from A to B, A is at positive potential with respect to B, is given by BLR. Okay, so now, so that's what we looked at, the voltage from A to B. The induced voltage from A to B is BLR times omega. Now, when the conductor passes through the left-hand side air gap, which is in here, so we saw that now it's going into the page. So we saw that the voltage induced is actually given by the top end positive and the bottom end negative. So we saw that how that's the second finger is pointing from bottom to top, right? Now, if you want to see which end is coinciding with A, it's actually the D, right? So if I want to see the voltage here, I can write voltage C to D is given by positive BLR times omega. So this is perfect correct. So as A coincides with B, if I want to write the same end first, like D first and the C first, then that voltage is given by E C to D, which is going to be negative BLR omega. So here there's a little explanation between how we do these voltages. So let's say here are the 2 points. This is the point A, which is at 8 volt. This is the point B, which is at 6 volt. Now, if I want to write E A to B, so that means it's 8 minus 6, 2 volt. If I want to write E B to A, so that is basically 6 minus 8, which is at 2 volts. So this shows that A is at a higher voltage than B. The first letter, which is used as a subscript, is always at a higher potential with respect to the second letter, which is used as a subscript. Okay, so here D coinciding with A, so that's why we're saying if we want to write E A to B, we're going to say E D to C to compare. But E C to D is having a positive voltage. At the same time, if you want to write E D to C, since D is exactly with the opposite polarity than A, so E D to C equals to negative EC to D, which is negative BLR omega. So ED to C actually is negative of EA to B. So that's for the two sides. When the conductor passes through this, so let's say conductor passes through this section in here, this one, or this section in here. So since there's no magnetic field, since we have assumed here B is 0, here B is 0, so that's why E is also 0. Okay, so now this is the graph for EA to B. Okay, so this is the graph for EA to B, only EA to B. So EA to B has a value BLR times omega when the conductor passes through the right hand side air gap. Now for the conductor passing through the left hand side air gap, if you want to just express EA to B on this graph only, so you're saying that equals to BLR omega. Okay, now when it passes through the left hand side air gap, so E C to D is BLR omega. If you want to express EA to B part, then it's going to be negative E D to C. See, the two ends are like this. So here we have to make sure that it has nothing to do with the complete coil voltage right now. It has to do with how A, B, C, and a D are. So A is at positive, B is at negative. Similarly, C is as positive, D is at negative. So when you're comparing D to A, they have the opposite polarity. So that's why the voltage from A to B is same as voltage from C to D, but it's negative of voltage from D to C. Okay, so here A to B is going to be negative voltage. Okay, the total coil voltage is given by the total coil voltage, so you can apply a small KVL in here. Let me see, what was the EC? So this was the EC. Okay, so that was the total coil voltage. So we can apply a small KVL like this, let's say. That KVL will give you negative EC plus EA to B plus the voltage B to C, which is 0, plus the voltage C to D, plus the voltage D to A is also 0. So that equals to 0. So that means EC equals to EA to D. So from here to here, right? Yeah. Equals to EAB plus EBC plus ECD. And that's 0. So it leaves EAB plus EC to D. You can express that. So EC to D here, you can exactly write just, so you can have this BLR omega. You can have this BLR omega as I showed on the previous slide. So that's going to just give you 2 BLR omega. That's the complete coil voltage in here, simply. Or you can go through a little bit of a complexity in here for no reason. So that complexity is, so what you're doing is you're saying EA to B plus EC to D. EA to B minus ED to C. So EA to B minus, why is that? Yeah. So D to C is negative of AB. So there you again have 2 EAB. So it doesn't matter. Or you can simply just say EC to D is the positive BLR omega, and simply twice as the BLR omega is the coil voltage. So the average value of the induced coil voltage is 0 in this case, right? Where is the coil voltage? So this is not the coil voltage I have drawn. So here I'm going to draw the coil voltage for us. That's only EAB. So let's say if I draw the coil voltage, it's going to look like this. Let's say that's 0. That's negative delta. That's positive delta. That's pi by 2. That's pi minus delta. Pi plus delta. So that's enough. And maybe one more, 3 pi by 2. Okay. So the coil voltage is what? When it goes from negative delta to delta. Yeah, so here what we have done is we said its value is 2BLR omega twice. So you can compare the amplitudes here as well. So in this case, the amplitude is BLR omega because we are doing the graph for EAB. In this case, the value is 2BLR omega. And you can see how the coil voltage is from A to D, entire A to D. Okay. So when it's from negative delta to delta, let's say, so its value is positive. Okay, so that's from A to D. That's from A to D, as we have seen in this diagram. Now the whole thing has switched its position. So one complete rotation has gone, let's say. So now what has happened is here was A, if you remember. Here was B, here was C, and here was D. So now the D, and C, and the B and the A has switched their positions, right? Because it has gone through a rotation. So once it has gone through a rotation, now you can see that your EC again, so your EC, that's the coil voltage in this case, is given by EDCBA, which is D to C plus C to D plus B to A, which is, again, for that part it's 0, and for rest of the two are there. So ED to C minus A to B, or plus EB to A. And its value is again 2BLR omega, which is from D to A now, but you can also see that it's E D to A is negative of EA to D. Okay, so here, negative of EA to D. So these commutator segments, what they do is they keep one side positive to the outside world, and then they switch from here. Whichever side comes positive, let's say this comes positive, it connects that positive to positive there. So now the D comes in here. So they switch this commutator segment in here so that it is again seeing the A as being positive. So the commutator segments each time switch, so that instead of having that coil voltage in here, it goes up, it flips, and now you're going to see all positive values. Okay, so now let's consider, instead of having one armature coil, we have two of them, and they're displaced mechanically at a certain angle, right? So that's why once we're going to have a graph, because this graph is according to, like, let's say minus delta delta and so on. So that's why now where you have those voltages appearing is also mechanically displaced with respect to mechanical angles. And as the coil voltage for one coil, for the two conductors, for one turn coil for the two conductors was the sum of the voltages across the two conductors. Similarly, when you look at the total voltage from the two coils, it's going to be the sum of the voltage from each coil. So you can see that it has started approaching, So it has started approaching more of a DC voltage, right? Because in the DC voltage, this is what we're expecting, something like this. And so that's what we're expecting. It's not only two coils, it's many of them. So that's why from the DC generator, you're going to have a constant DC voltage produced. Let's calculate the average value of the induced voltage from one coil system. Still one coil system, so here is the graph, and we're calculating its average value. So now it looks like we need to have the graph. So this is how the graph looked like actually. Okay, so this is how the graph has looked like. All right, and this value is 2BLR omega. So the average value, you can consider any one cycle, and in this case, we're considering a cycle from 0 to pi, let's say. That's one cycle. You can consider from negative delta to pi minus delta as well. So this could be considered as one cycle too. Okay, so you do the for finding the average value, you take 1 over pi, the length of the cycle, and you integrate the function e over the entire range of the cycle angle we have considered. So you have e from 0 to delta, the value of the function d theta, plus from delta to pi minus delta, it's 0. So from delta to pi minus delta, and then from pi minus delta to pi, you again have the function value times d theta. Okay, so from here you have delta. From there you have pi minus delta, which is going to give you positive delta again, this one. Okay, so that's what you got. Now we're looking at the air gap cross-sectional area. So air gap cross-sectional area with the radius r, of course, and the angle spread of 2 delta. So the area is given by r, 2 delta times L, the back length. So we're going to replace that 2r delta L with A. And now this B times A is your flux for the constant magnetic field. And phi is the flux that passes through the air gap under each pole. So for a coil, that's the EMF, the voltage induced in the armature coil with 1 turn. If you have a coil with n number of turns, then it's going to be 2 multiplied by n, because voltage induced is directly proportional to the number of turns. And this factor 2n over pi, we're going to consider it as a constant k, which is called the machine constant or armature constant. That depends on the type of the armature winding, the number of poles of the field, number of coils, number of turns in each coil. So E, induced voltage, and for simplification purposes, we're going to take that bar off. We're going to just simply say E, which is the induced voltage. So this is called induced armature voltage, is given by K phi omega. So where phi is measured in Webers, omega is measured in radians per second. Phi is the magnetic flux produced by each stator pole, and omega is the angular velocity of the rotor, or angular speed of the rotor, in radians per second. So induced armature voltage, also called internally generated voltage in the machine. So here is an example which we're going to look through. Okay, so we're looking through an example that says in a particular type of the winding known as the lap winding, the constant K is given by Z over 2 pi, where Z is the total number of conductors. So that will help us finding K. In the armature, of course, if the DC machine has 90 lap wound coils, each having 4 turns, and if the air gap flux is so phi is given 0.04 in Webers. So we'll be looking at to calculate the E. So when we're calculating E, it equals to K phi omega. So let's make the calculation of K first. So Z is the total number of conductors. In order to have Z, we have 90 coils. Each coil has 4 turns, and always one turn has 2 conductors. Since we're going to be looking for the number of conductors, so it's going to be 90 times 4 times 2. So that's one thing. The second thing is to see the speed is represented by N is given in RPM. So RPM is the rotations per minute. But in the equation we have omega and radians per second. So how to relate those two? So one rotation equals to 2 pi radians. And if you say 1 rotation per minute, it could be 2 pi radians per minute. And if you want to do 2 pi radians per second, it's going to be 2 pi over 60 radians per second. All right. So 1 RPM, rotations per minute, is going to be 1 over 60 over 2 pi radians per second in here, right? And or we don't need to go up to, and there we are okay if we just leave it here. This should be fine. Now, so in order to convert 600 RPM, so 600 RPM is going to be what in radians per second, okay? So it's going to be 600 divided by 60 over 2 pi in radians per second. Okay, 600 RPM. So then our E, it will be K, which is 90 times 4 times 2 divided by 2 pi multiplied by 5, 0.04, multiplied by the speed, 600 divided by 60 over 2 pi. So all of them known, and it comes to 287.6 in volts. So the units of the voltage is volt. Okay, so we have the magnetization graph of a DC machine. We're gonna figure out how the induced voltage is related to the field current in the DC machine. So we saw E depends on K, depends on phi, depends on omega. So this is constant, machine constant. So for any one speed, if you make that constant, E is proportional to phi. And where is this field produced by? This field is produced by the field winding current. And the current flowing through the field winding, let's say, is represented by IF. Let's say is represented by IF. So phi depends on IF. So that is how E indirectly will be proportional to IF. So here on this graph, you can see the field produced by depends on the current in here. So that's the MMF, if you can relate, which is given by NFIF. So number of turns in the field winding and the current flowing through the field winding. So MMF produces the magnetic field. Since we said flux is proportional to IF, so E is proportional to field phi, and so E is the y-axis can be replaced by E on this graph, and the x-axis can stay as IF. So for any one speed, let's say you talk about omega equals to omega 0. So this graph is between E and IF now. So for any one speed, E is proportional to IF for non-saturation part. Okay, so under the saturation part, we have to look at the graph because the change might not just be proportional. Okay, another conclusion which we can make in here is for one constant current. So again, E, if you keep IS constant, E is proportional to omega. So if you keep IF constant. So since they're proportional, so let's say here was omega 0. Now you lower the speed to half of that. So that means this graph is going to be shifted down. So that means if E0 is corresponding to omega 0, as proportional to omega 0, okay, let's do it like this. So E0 over E1 equals to omega 0 over omega 1, proportional to speed. And since this is the ratio of the two speeds, so it doesn't matter you put it in radians per second or you put it in RPM. So you can also do it N0 over N1. So that's the proportionality, which is very, very useful. Okay, we're looking at the DC machine torque now. So that's the torque produced by the machine. And torque is the rotational force, actually, force times the distance. And since it's rotating. It's doing the rotational motion. So we're going to see from the center, it's rotating through a distance of r, the radius r. So that's why torque is going to be given by force multiplied by r, and the force, as is known, is given by 1 on one side. The current flowing, the magnetic field, the length of the conductor. Okay, so you can see the direction of the force is going to be given by left hand, is it? Yes. Okay, so with the left hand, you have the first finger as the direction of the field, and the second finger is the direction of the current, and the thumb gives you the direction of the force. So you can see how that's the first finger, how this is the second finger, and how thumb is pointing out of the page. So that's the thumb pointing out of the page. Okay, pointing out of the page. Okay, so you can see that's the torque for one rotation from negative delta to delta, and it's going to keep repeating itself. So in one cycle, that's the torque. In order to calculate the average value, we're going to use the same procedure as we have used for the voltage. So the average value of the torque is average over one cycle. And where are we getting the cycle again? So this is going to be considered as one cycle. One cycle is where the wave starts repeating itself. So this is where it has started from, let's say. And you're going to see that after one cycle, that is where we are stopping at. Okay, so from 0 to delta, it's the function's value. From delta to pi minus delta, it's 0 function's value, the torque value. And again, from pi minus delta to pi is again the value of the torque is 2 IALB. d theta is the variable for integration. Okay, so after you go through the area and the use of flux for representing B times A, you're going to end up having the average value of the torque. And for simplicity, again, we're going to remove that bar from the T. So the torque produced in the machine, or the induced torque in the machine, is given by 2 Ia phi over pi. So 2 over pi Ia phi. And for n number of turns, it's going to be 2n over pi Ia phi. Okay, and this is the same constant as you have in the induced voltage equation. So that's the same constant, the machine constant or the armature constant, phi and Ia. And this is the armature current, keep in mind. So T is the induced torque measured in Newton meters. K is the constant, phi is the flux produced by the field winding in Webers, Ia is the current flowing through the armature coils, and is in amperes. So that's the second equation which we have developed. Okay, so this is how we represent the DC machine using a model, using an electrical model. So the DC machine has two windings, the armature winding and the field winding. Field winding do not have any source of power. That means it does not induce any voltage in there. What all it does is it takes power from the external source. So that's the external source, external electrical power. External source. So that external source is feeding the field winding, and once the current flows through the field winding, it produces the magnetic field. That's all the function is. That's why it is represented by a resistance and an inductance. Okay, so F as a subscript is used to represent the field winding quantities. So for example, VF is the voltage applied to the field winding, IF is the current flowing through the field winding, RF is the resistance of the field winding, LF is the inductance of the field winding. On the armature terminals, there is a difference. So here are the terminals. First of all, here are the armature terminals where they are connected at the brushes. Okay, So now what is happening in the armature winding? It still has the resistance and the inductance because it's the same type of winding as the field winding is. But in addition to that, there's a voltage induced in there. And we saw that the induced voltage is represented by a source of the voltage the way it is in here. So E, and the value of that internally generated voltage or induced voltage is given by K phi omega. Okay, so that is how you represent the armature winding, the resistance, the inductance, and the induced voltage. So this is the internally induced armature voltage. Okay, this is also armature voltage, but that's called armature terminal voltage. Okay, now the induced armature voltage, or it's also called internally generated armature voltage. And one more thing, internally generated voltage, armature induced voltage. Okay, what else it is termed as? Now, how is this E different than VA? How is this E different than VA? Let's say there is so this E is different than VA with the drop across the resistance. First of all, under steady state conditions. Steady state conditions. The voltage across the inductor, let's say you say VLA is 0. The voltage across LF is going to be 0. Why? Because the voltage across the inductor is given by L di over dt one way. You also have the change in flux as well. So under steady state, this I is constant, which gives you di over dt equals to 0, which gives you VL equals to 0. And this VL0 is same as a short circuit. So that means under steady state, these inductors can be just replaced like this. Like this. And this analysis, this whole course afterwards as well, is under steady state. So that's why it's only it will be in analysis, it will only be RF, RA. Somewhere when we're doing the power electronics control of machines, that is where this L still plays its role, because we look at the conditions where we're not only running under steady state. Okay, so what I was saying is, what is the difference between E and VA? So if you try to see, the difference between E and VA is the drop across this resistance. Let's say in one condition, let's say this is how the current flows. Okay, so that's going to give you a voltage drop like this across it. So now you apply KVL in any direction, doesn't matter. So that KVL will give you negative VA plus RAIA plus E equals to 0. So you can see the difference between E and VA depends on this drop. Oops, sorry. Undo. Okay. This drop, right? It's given by this drop. Now let's say under certain condition, this IA goes to 0. We're going to see what that condition is called. If that IA goes to 0, that means E equals to VA. This condition of IA goes to 0 is called open circuit or no load condition. So we call this condition of IA being 0 as open circuit or no load condition. Open circuit is clear to everyone, so current goes to 0. The no load, to explain, is when the mechanical load does not want any current to be supplied by the machine, or the mechanical load is not supplying anything into the machine, depending upon motor or generator action. So this condition of IA equals to 0 is called open circuit or no load condition. So that means under open circuit or under no load, E basically is equals to VA. So that means by definition, E is also called open circuit armature voltage or no load armature voltage. So all these are names for E, which you're going to see different at different times. And VA is called armature terminal voltage. Here we have two different systems. One is when the machine can work as a generator. The second is when machine can work as a motor. So in case of a generator, machine actually supplies the load to these points. And that is how you can see the current going out from the machine into those points. In case of motor, the machine takes in the current from the external source into the machine. So that's why you see the current coming from those points into the machine. Okay, so that's the motor and that's the generator. Okay, so so a quick KVL in here. So that quick KVL, so that's the motor. Sorry, that's the generator, my apologies. Minus VA, and with that direction it's like this. So minus RAIA plus E goes to 0. And what you got is you got VA equals to E minus IARA. Similarly, let's say I'm doing in here the KVL. So KVL in this case will give you negative VA, and with this polarity of the current, it's going to be top end positive and the bottom end negative. So that's going to give you RAIA positive plus E equals to 0. So that will give you VA equals to E plus IARA. So you can see in case of generator, how E is larger than VA, and in case of motor, VA is larger than E. So that means in case of generator, E is the internally generated voltage, which takes care of the voltage at the terminals plus any losses at the resistance level. In case of the motor, it's the external supply which takes care of the voltage generated inside the machine, which in this case will not be actually the generated voltage. We're going to call it back EMF or counter EMF, because that is what the external supply has to take care of in addition to any losses through the resistance. In case of generator, it is called the induced voltage. In case of motor, it's called the back EMF, counter EMF. Okay, so the developed torque or the torque is given by K phi Ia. And again, in case of motor, it's called the developed torque because it is required to rotate the machine. In case of generator, it is not required. It is in opposite to the external load torque. That's why it's called opposing torque. Right? In case of permanent magnet DC machines, the field circuit is not there. So that's why K phi is fixed by the magnets in case of permanent magnet machines. So in case of permanent magnet machines or motors, the field is supported by magnets mounted on the stator. Characteristics are similar to separately excited machines. So separately excited machine are where the field winding and the armature winding are separate, and the field winding has an independent source of supply than the armature winding. But in case of permanent magnet machines, the field cannot be adjusted. The value of the magnetic field cannot be adjusted. So advantages: no power is required to establish the field, the magnetic field. So efficiency is better and the size is also smaller. Disadvantages are the magnets can become demagnetized by overheating because of the excessive armature current. Flux density amplitude is smaller in comparison to electromagnet based machines. Torque produced per ampere of the armature current is smaller. The permanent magnet in case of permanent magnet motors than in the field wound machines. Applications: it could be used as fractional or sub-fractional horsepower motors. So horsepower is actually the capacity of the machine. It's one way to measure the wattage of the machine. 1 horsepower is actually 746 watts. So wattage is the power. Okay, so when you're looking at how much power this machine can handle, so mostly because usually it comes with the large numbers in watts, so that's why it is expressed in horsepowers. But when you're looking at fractional, sub-fractional, so that means you're looking at 1/4, 1/8 of an HP and so on, not like 20 HP, not like that. So the applications for the permanent magnet machines is in the fractional, that means the small machines, like for example in the fans or in the power windows of the automobiles. Okay, so we're looking at the power flow, how there's a power flow in electrical machines, in DC machine in fact, and we're looking at the generator first. So in case of a generator, what does a generator do? Generator takes in the mechanical power. So generator converts mechanical power to electrical power. Electrical power. So mechanical power is supplied at the shaft. Okay, so mechanical power is supplied at the shaft. So that's why the input power to the generator is at the shaft, is also called P shaft. And the power can be, so soon we're going to come in here. So power can be expressed as the torque multiplied by the speed. So that's why we're going to say the power at the shaft, or the input power to the generator, is given by the applied torque multiplied by the speed, the rotational speed, the angular speed in radians per second. Okay, then goes off are the rotational losses. Okay, mechanical losses or rotational losses. So then goes off is the taken care of is the mechanical losses or the rotational losses, and core losses are actually a part of the rotational losses or the mechanical losses. Okay, so they're not separate all on the drawing. I draw them separately, but they're a part of the rotational losses. Okay, then you reach where do you reach? You reach the air gap here. So here you're at the air gap after the shaft between the external connections and the rotor. So you take the rotational losses off from the rotor, and then comes the air gap. And the power at the air gap, you can write it as air gap power, like AG is for the air gap, or the power at the air gap is also called the developed power. So this D is the developed power. After the developed power, you take care of the electrical losses. Now the electrical losses are given by I square R losses actually. And where will that happen? That happens in the resistance. And where is that resistance present? That resistance is present in the armature. So armature current square multiplied by the resistance of the armature. You might be thinking there is a field resistance as well. So in some of the configurations later on, we're going to be discussing about 3 different configurations of the DC machines, which is separately excited, shunt, and series. So you actually take off in case of shunt and series, you take off the field winding loss, and most of the times in separately excited you don't consider it, so that's why it is not shown in there. So from the exam perspective, let's say, so you will be explained, do you ignore the field winding losses, or otherwise you can consider them as well. So from here you can also be looking like this, IF square RF, let's say. Okay, there we are. So we are at the output terminals now. So that's your output power. That's your output power after you took off the electrical losses. So the output power is at the, so this is where you are now in the electrical system. Electrical equivalent circuit. This is how your electrical equivalent circuit looked like. So in case of generator, these are the output terminals. And this is the shaft, let's say. This is where your load is going to be. Okay, so this is where the input is. You're gonna say here is your input, which is at the shaft. Then shaft rotation, rotor. So rotational losses. This is where comes the developed power. which can also be given by E times IA. Okay, so here are the electrical losses, and this is where your output power is. Okay, now the developed power is given by P output plus the losses, the electrical losses. And the output power is given by VAIA. The losses are IA square RA. So you take IA common from both of them and you're left with that. And that gives you E times IA. So this is your developed power E times IA, as I wrote in there. And that's given by, you can express E as K phi omega for the induced voltage times IA. And from there, K is there, so IA is there, and phi is there. So this portion is your T, so T omega. And since we're talking about the developed torque, so this is the developed torque. In case of generator, it is the opposing torque, which is balancing the torque of the mechanical mover, okay? In case of motor, it will be the developed torque. So from there, we saw that how P, so this was your P developed, equals to T developed times omega. And you can actually, this is a generic expression, T times omega, and it can be applied at any level. Now we're going to look at the power flow in the motor. So in case of a motor, it's a little different. So again, let's start with the equivalent circuit. So in case of motor, this is where the power supply is applied. So this is where the input power is coming from. So we're going to say here is the input power, which is going to be given by VAIA, and it's the electrical power, and the current is going to go into the machine. Okay. So the first loss which will happen will be here. So this is where will the first loss happen, which is the electrical loss this time. Okay, so where starting point is here. The electrical loss then reaches here. So this is again the developed power, which could be E times IA, and it is the power at the air gap. After that, it goes through the rotor. So again, here are the rotational losses gone. So mechanical loss or rotational losses. Okay, and then comes here at the shaft. So power at the shaft now will be your output power, and that will be your load as well. So that's the power flow in here. And you can see how the developed power is given by, where is the developed power? Here is the developed power. Is given by the input power, VAIA, minus the loss in here. So take IA common again. So that gives in here. And you saw that this is E, and E substituted as K phi omega. So this is again T times omega. So you can see P developed equals to the D developed times omega. And here this is the developed torque, which is produced by the motor to move the load. Okay, so 3 different configurations for the DC motor. One is called separately excited. So in case of separately excited motor, you have a field winding fed from a different source than the armature winding. So armature winding is fed from a different supply, and the field winding is different from a different supply. And under steady state conditions, so that's for steady state, SS steady state. So under steady state conditions, this is a short, or you can say that the inductor has a 0 value, or the voltage drop across the inductor has a 0 value. So in case of separately excited machine, you can see using Ohm's law, VF, the voltage applied equals to RF IF. And here's the current flowing through the armature, and was the same current as it's taken from the supply. So T is basically terminal, the current taken from the power supply terminals, the voltage at the power supply terminals. VA is the armature terminal voltage. CVT is the supply terminal voltage. All right, and you can see, again, it's a repetition, although. So you can see negative VA plus RAIA plus E goes to 0, or VA equals to E plus IARA, IA equals to IT, VA equals to VT. All right, so, and you remember in case of a motor, so this is the motor configurations, right? And in case of a motor, if you remember from the linear machine, let's say this was the conducting bar. So this was the load force. Sorry, my apologies, it was exactly opposite. Okay, let's do it like this. So there was the load force, and this was the direction it was going in. So that was the force produced by the magnetic field. So that's why you can see this is the load torque, and this is the developed torque. Okay, that's why they're drawn in opposite directions. Okay, and then the next configuration we have is the shunt DC motor. So in case of shunt DC motor, both the field winding and armature winding are supplied from the same power source, and they are connected in parallel. So field winding and the armature winding are connected in parallel. So you can see the same point, a split, and they go back and meet at the same point. So from here, split take two different paths. Here, come back to the same point, and there. So the field winding and the armature winding are connected in parallel. And you know, across the parallel connected points is the same voltage. So that's why the voltage between these 2 points is the same. So that's why you're going to have VA equals to VF, and that equals to the supply terminal voltage. Another thing which you can see if you apply KCL in here, so you're going to see the current entering is IT equals to the two currents leaving, IA plus IF. Okay, so that's the second thing true for the shunt DC configuration, shunt DC motor configuration. The last configuration you have is the series DC motor. So in case of a series DC motor, you have the the field winding and the armature winding connected in series. So when you're connected in series, so that means they're connected on one path. So you start from here from the power supply, and that's the main current from the power supply as IT. So that's the field winding on the same path. It doesn't matter if I have drawn this up and down, doesn't matter, you can just draw them in one line, okay? And then you have the armature winding on the same path, and there we are. So it's only one single path. That's why it's called a series DC motor. And in case of series connection, you see the same current. So that's why all the three currents, the current flowing through the field winding, the current flowing through the armature winding, and the current taken from the supply are equal. And another thing, if you try to apply the KVL, that will give you negative VT plus VF plus VA equals to 0. Or you have VT taken care of the two voltages, but both of them, so they are not in parallel. So they are VF plus VA equals to VT. There are some things which is common among the three types of configurations. There are a few things which is different. So the three different configurations of DC motor. Here's a question we're going to discuss. So we have a DC machine that is used as a separately excited generator. So it's a separately excited generator. It has an armature resistance of 1.5 and generates an open circuit voltage. So open circuit voltage is E, 200 volt. And the speed, the speed at which it is generating that open circuit voltage generates an open circuit voltage of 200 volts at a speed of 1200 RPM. Okay, and it's a generator and it's separately excited. So this is how the diagram will look like, and I'll skip to draw the inductor. And since it's a generator, so I'm going to have the current flowing from the machine into the external terminals. R is 1.5 ohms. E is 200 volts. So first part is we need to calculate the terminal voltage under a load of 5 amperes. Okay, So we have to calculate this, but not at no load. It is at under a load of 5 amperes. So we're gonna apply a KVL, or if you know the equation, you can make use of the equation without applying KVL. So VA minus RAIA plus E equals to 0. So VA equals to E minus RAIA. So since it says under a load of 5 amperes, so that means this is going to be 5 amperes when we're calculating it. So E is 200 volts minus RA is 1.5 multiplied by 5 amperes is the load current. And that gives you the value of the terminal voltage. And you can see that E is taking care of the terminal voltage as well as the loss across the resistance. That's what part 1. Part 2 of the question is we're looking for the opposing torque because this is the generator that the machine produces. So we're looking for the opposing torque, which is given by K phi IA. Now what we know is we actually don't know much of this stuff. But what we can do is we can make use of the equation E equals to K phi omega. So E is 200 equals to K phi. Speed for that 200 is 1200 in RPM. So we're going to divide it by 60 over 2 pi to convert it to radians per second. So that's going to give us the value of the K phi. 1.592. And we're going to bring it back in here saying T equals to K phi multiplied by 5. 7.96 Newton meters. Part 3 of the question is we're looking at the efficiency of the process, ignoring the energy loss of the field winding. So efficiency is given by the output power to the input power ratio in all cases. Now this is the generator. So for generator, the output is here. So this is where output is. And again you connect it to the shaft. So the shaft power is its input, and you guys know from the power flow, after the input power you subtract the rotational losses. That gives you the developed power, and from the developed power you take out the electrical losses, and that gives you the output power, right? So that means now in this case rotational losses are not given and we don't have any way to calculate, so we're gonna just assume that they are 0. So in that case your input power is your developed power. So developed power, everybody knows that is here, which is E times IA. So you can solve it this way. So you can say this is E times IA over VAIA times 100%, which is actually E over I simply. So which is E, which is, sorry, did I do anything wrong? Sorry, output. Yeah, so I just made a mistake writing in here. So in writing, P output is actually VAIA, and the developed power is E times IA. So that's 192.5 times 5 over 200 times 5, and that gives you approximate number of 96.25%, I believe. Okay, another question. Okay, so here in this question you're given the graph between I, so that's your field current in amperes, and E, and that's given for speed. So this graph is observed at a speed of 1500 RPM. The RA is there. The open circuit armature voltage at IF well, that's what we have to calculate. So we're calculating part 1, open circuit armature voltage is E at IF 2.5 amperes and a speed of 1200 RPM. So we're going to make use of the table. We can get E at IF equals to 2.5 amperes from the table, whereas that this is the value. But that is also for a speed of 1500 RPM, not 1200 RPM. So that E is 140 volt for 1500 RPM. So then, since the field current remains constant between these two, right? Says the field current is constant because we basically found E140 for a speed of 1500 RPM for 2.5. Now it's asking us to calculate the same E for the same current for a different speed. So we're going to use this relationship E1 over E2, let's say, is omega 1 over omega 2 equals to N1 over N2. So let's say we're going to consider all these as 1s and these ones as 2s. Okay, so that means E1 is 140, E2 is not known, equals to N1 is 1500 RPM and 2 is 1200 RPM. So that gives you the value of E2 as 112 volts approximately. So it's 111.83 volts, approximately 112 volt. Second part of this question we have is the machine torque under the condition of part 1. And we are also given this as 20 amperes. So we have to calculate T, which is given by K phi IA. So K phi we can calculate from part 1 because it says we're calculating torque for the conditions of part 1. So K phi is E over omega, which is E, you can take E as 140 and N as 1500, or omega corresponding to 1500, or you can also have it from 1200 as well, because for 1200, for 1200 we have calculated it as 112 volts. So you can consider any of the cases. Let's say we calculated from 140. So for 140, it's at the speed 1500, and we're gonna say 60 over 2 pi. So K phi is 0.89. So then your T is going to be K phi. Sorry, I don't need to write that again. 0.89 multiplied by 20. And that gives you 17.8, and the units are Newton meters. So that's part 2 of the question. Now we're going to lead to part 3 of the question. Okay, so part 3 of the question, the machine armature terminal voltage here we are finding VA, which is if the machine works under the conditions of part 1 and part 2 as a generator. So whatever the conditions are given in part 1 and 2, they will be true. What we mean by that is we have IF 2.5 amperes, we have speed 1200 RPM, we have E 111.83 volts or 112 volts, and IA is IA was given in part 2 as 20 amperes. So it's saying working as a generator. So this is how it's going to work as a generator. So in case of a generator, it supplies the armature terminal. So this is how the flow of the current will be. That's the main difference between the operation of the motor and a generator. And that is how the polarity of the resistive voltage drop will be like this. So now you can apply KVL because we're finding VA. So negative VA, negative RAIA plus E equals to 0. So VA is going to be E minus RAIA. So E, let's say, is 111.83 minus the value of RA is also given to us 0.15, so here it is, okay? Times IA, which is 20. Okay, so if you solve for that, that gives you 108.83 in volts. So that's the case of a generator. Part 4 of the question, let's use it with a different, solve it with a different pen. The armature terminal voltage, again, if the machine works under the same conditions, so all this is same, but now it's going to work as a motor. So in order for it to work as a motor, the direction of the current is going to be from the terminals into the machine. And that is how it's going to provide the polarity of this drop as like this. Okay, so again we can apply KVL and that will give you minus VA plus RAIA plus E goes to 0. So we're calculating VA, which is E plus IARA. So E is 111.83 from part 1 and 2 minus, no, plus 20 times 0.15. So here VA is going to be higher than E, so 114.83 in volts. Okay, we have another example, and this is for a shunt motor. Okay, so this is for the shunt configuration. And here it tells you a 50 HP. So this 50 HP, and it's a DC motor, this is the rating of the machine. Rated power. So rated power, the machine may not run at that particular power. It may run below this value, or it can run sometimes overload as well, so by a certain amount. So rated power, a 50 HP, so that's going to be on its nameplate. A shunt connected DC motor has the magnetization curve shown in this graph in here. The DC supply voltage is 240, so that's the 240 volts. The armature resistance is 0.065. The field resistance is 10 ohms. And the adjustable resistance is 14. So there is an adjustable resistance in the field winding, which is set to a value of 14 ohms at a speed of 1200 RPM. So all this is happening at 1200 RPM? No, not all this is. So those are the variables or parameters at a speed of 1200 RPM. The rotational loss is 1450 watts. If the motor drives a hoist that demands a torque of 250 Newton meters, so here the units are Newton meters. So if the motor drives a hoist that demands a torque of 250 Newton meters independent of the speed, determine the motor speed and the efficiency. So it's looking for to develop that, what speed the machine has to run at, or machine has to drive at. And we're going to be also calculating the efficiency of the machine. So in order to solve for this, so we are finally looking for the speed before we calculate the efficiency. And in order to calculate the speed, it looks like we have to work through the torque, what the torque needs to be developed by the machine. So here to understand, it's a motor. Okay, guys. And in case of a motor, so motor takes in the electrical power and develops the mechanical power at the shaft. So here is the input, electrical input power, which is going to be given by, in this case, it's VT equals to, you can say, so input is here. So these are the points where the input power is. And it's applying both windings, right? So it's going to be voltage at that point multiplied by current at that point. So that's going to be the input power. Then we're going to subtract. And we're going to take care of, so this is the electrical power input. The loss is the electrical loss. So in this case, it can be the losses present in both bindings. So one could be IA squared times RA, the other could be IF square RF. So sum of them. That gives you the developed power. After that, so you subtract the rotational losses, and that gives you the output power, which is same as the power at the shaft, okay, which is same as the power required by the load, let's say. So we have an equation P equals to T times omega. So this equation must be used for the corresponding quantity. What I mean to say is, if you're writing here P output, then this T has to be T output. If you're using it at the power developed level, then this has to be the torque developed. Let's say you can also relate the rotational losses. So here is going to be the T rotational times omega. So we're going to start looking at what is the E in this case. What is the induced voltage, or what is the internally generated voltage? In order to calculate for the E, we're going to make use of this graph. So in order to make use of this graph, we need to calculate what is IF. So in order to calculate IF, we will use Ohm's law. We'll say what is the voltage here, which is 240 volt. So that's the total voltage, and the current flowing through that branch is going to be the total voltage 240 divided by the total resistance, which is going to be 14 ohms and 10 ohms. So IF will be calculated as 240 the total voltage divided by 10 plus 14 the total resistance. So that gives you 10 amperes. So then we're going to go in the graph in here. We're going to say that's the 10 amperes IF, and we go to the curve, and we have the voltage as 280. So here the internally induced voltage at the armature is 280 volts. And the machine speed 1200 RPM has a rotational losses of 1450 watts. So we're gonna reach up to, we are given the load torque, but we're gonna go up to the developed torque equation first in order to calculate what will be the current drawn by the machine at this level. Okay, because we will be looking for the speed in the end. So the steps we're gonna follow. So we have IF and E, and we have the speed. So with that E and speed, we will calculate K phi. Once K phi is calculated, we will be looking forward to the calculation T developed equals to K phi times IA. And with that, we will be able to have a numerical value for the current IA. And then we will lead towards the speed with the new E. Okay, so in order to calculate IA, we need T developed. In order to have T developed, that's the sum of the T output and the rotational torque. T output is given to us, and we can make use of the equation P equals to T times omega. So P rotational equals to T rotational times omega. T rotational we need to calculate. P rotational is 1450 watts given at a speed of 1200 RPM. So we'll calculate that. Sum up in order to calculate what should be the developed torque by the machine. And since this equation and this equation T equals to K phi IA, the torque is always only the developed torque. So this you can't do. T(n), let's say. You can't say K phi IA. This is incorrect. Okay, or let's say you're gonna say T output equals to K phi IA. So this will be incorrect in case T rotational is not 0. If T rotational is 0, in that case you can have T developed same as T output, and now you can have it as K phi IA. Okay, so we calculate the value of the current. With that value of the current, we can calculate E. E equals to the terminal voltage minus IA RA. So 240 fixed, IA calculated, RA is also fixed. So that's the new value of the E. And with that new value of the E, with the previous value of K phi, because K phi now depends on And the field current, since the field current is constant, so you're going to have your K phi remaining constant as well. So that's going to give you your new speed. So this is the speed at which the machine will develop a torque to the load. Machine will develop a torque of 261.54 Newton meters, and it will provide the load a torque of 250, because 11.59 will take care of the rotational losses. Okay, so with that, the second part, we need to calculate the efficiency. In order to calculate the efficiency, it's again the P output divided by P input. And P output is T output times omega, because this time we know the load torque and we know the speed the machine is running at. And now the machine is running at this speed, okay, not 1200 RPM anymore. So 250 is the load torque, is the output torque, times the speed from here. And the input we already said is the terminal voltage times the terminal current, so 240. So that's your field current, plus this is your IA, so that's your IT. So P output divided by P input gives you the efficiency. You might have some other ways to calculate it as well, so it's fine if you use some different methods than this. Okay, so now we're looking at the torque speed characteristics. Torque speed characteristics first is going to be, so where we're going to relate speed as a function of torque. So this is the case of a separately excited DC motor, and these are the equations which we have developed before. So T equals to K phi IA and E equals to K phi omega. So that's the induced voltage and the developed torque. And also for the motor, this is the motor, okay, motor. E plus IA RA equals to VA. So now you can substitute the expression for the E, the expression for the IA in there. So expression for the E is substituted as K phi omega, and RA is kept as it is. The expression for the IA is used as T over K phi from here. And so we want speed to be a function of the torque, so that's why we're manipulating this equation. When we're manipulating, so we're going to say it's going to be VA minus K phi omega, and the whole thing multiplied by, we want the speed. My apologies. Okay, let me erase. We want the speed on one side, so it's going to be VA minus RA over K phi times T equals to K phi omega. So divide both sides by K phi. Equals to omega. So that's going to be the equation, and that's the required equation in here. And you can see, so that's your Y, and this is your X, and that's let's say as M. Okay, that's your X variable, or let's use some other color pen for the constants in the equation. And it's minus, and let's say this is M, and this is C. Okay, so this is the equation of a straight line where you see a negative slope in here. So that gives you the negative slope for the straight line graph, and this gives you the y-intercept, right? Intercept. All right. And again, one more time, so this torque is the developed torque in this equation, okay? Is the developed torque. Okay, what else? Now, so the graph for the speed versus torque is here, and this is the T developed, never forget about it. So when, for this point you have T equals to 0. And T is what actually? T is the load at the machine, which is making machine to do some work. If you don't put any load, then it won't develop any torque. So this point actually corresponds to torque equals to 0. So if this point corresponds to torque equals to 0, so that means here the speed point which corresponds to this point in here, that's called a no load speed. That's called no load speed. So T substitute equals to 0. So the no load speed is going to be VA divided by K phi. Okay. Another point to observe is this point on the x-axis. So this point corresponds to no speed. So 0 speed. So 0 speed of a machine is interpreted as called standstill. Standstill. So the machine is not rotating, machine is not moving, standstill. Or it's also called stalled. So the machine is stalled. And since it's the torque point, so it's called the standstill torque or the stall torque. And again, if you substitute omega equals to 0, it's going to give you a value for the torque, which is given by, so you're going to substitute omega 0. Omega equals to 0 gives you VA over K phi equals to RA over K phi square times T. Okay, so we're calculating T. So that cancels. And T goes to VA over RA times K phi. So that's your standstill torque. So that's the torque speed characteristics, which we will make use of once we will be doing some speed control. And there we are at the speed control actually. So what is the speed control? Now, this was the torque speed characteristics, the operating speed. How is the operating speed decided? So the operating speed of an electrical machine is determined by the intersection point of its torque speed curve and the torque speed curve of the load. So here are the characteristics of the machine. Now, which machine it will run at, what will be the operating speed? That's decided by the intersecting point of the load characteristics and the machine's characteristics. So this torque speed characteristics of the load is dictated by the application, is dictated by the load. Okay, so for this, the operating point is given by omega 0 T0. So T0 is the torque it has to take care of. To take care of the torque T0, it has to run at omega 0 radians per second speed. So in order to change the speed, the load remains constant, meaning it depends on the application. So you can't change this blue graph. What you can change is the purple line in order to change the operating point, in order to change the intersection point. So to change the speed, the torque speed characteristics of the motor or the machine must be changed. And now we're going to see what we need to do for doing that. Okay, since the equation is like this, so equation is omega equals to VA over K phi minus RA over K phi square times T. So we're gonna how to change the torque speed characteristics and how to change that intersecting point. So whatever the speed depends on or is a function of, we change them, so the graph will change. So number one is to change VA, this factor in here. That's called number one. Change armature voltage. That's called VA is the armature terminal voltage. So you change that, there will be a direct change in the torque speed characteristics. But one thing which you see, this was the y-intercept. So if you change VA, it's going to only change this part, which is the y-intercept. It will not make any change to the slope. So slope will remain the same. Will only change y-intercepts. So that's the y-intercept from here to here to here as you are lowering the value of the VA. And the operating points will change from 1 to 2 to 3. Now this is a very efficient method as it does not lower the efficiency of the operation as it does not involve any resistance, because resistance leads to heat loss or the loss of power. But at the same time, how we will implement this, because we want the VA to have different values. So far we saw that the power supply which is supplying the armature is coming from a fixed power supply source. Let's say you have a battery of 12 volts as an example, which is feeding a very small motor. In order to implement this armature voltage control, we need to have the variable supply, and that's a very expensive method. Okay, so it's efficient, at the same time it is an expensive method. Okay, number 2 is what else we can change? We can change RA. So that's the armature resistance. So that's the second method in here, armature resistance. Now with the armature resistance, you can see that it will only change the slope, but it will keep the y-intercept same. So here the y-intercept same, because that does not involve RA. So since omega is proportional to RA, so RA is in the numerator, so you're gonna see as we're increasing the value, we're increasing the slope. So this is the smallest slope, and that's the largest slope. So smallest slope, and this graph has largest slope. All right, so VA gonna remain same, and the field current will remain same as well. But since this involves increasing the value of the RA, so there is a loss corresponding to RA, which is RIA squared times RA. So it's going to increase the amount of the loss, the power losses, and that is how the efficiency will be low. The third method we have is the KFI factor in here. KFI. So let's write K5 first, and then, so we're saying the third method is to change K5. And the very first thing we observe with respect to K5, so K5, that it is a part of both the y-intercept and the slope. So you can see if we are changing K5, it changes these points, which is the intercepting points, and it changes the slope as well. So slope of this line and slope of this line to compare are different. So it impacts both parts of the graph. And since K5 is in the denominator now, so as you're increasing the value of the K5, so you're increasing the value of the K5. Okay, so if you see, in case of VA, it was decreasing, the points were going down. Now you're increasing K5 and the points are going down. So you have K5 larger than K5 2 larger than K5 1. This is how they are. Okay, and the values are going down. Now this method, since it involves the field side, so it cannot be used for the permanent magnet machines where you have the K5 value as fixed. Now how will the K5 could be changed though? K5 is on the field side, and this is how the field side looks like. LF does not matter though, but still I have drawn it. So K5 is a function of the field current, and field current is given by VF over RF. So it can be changed by changing the voltage, it can be changed by changing the resistance. Okay, so change in VF or change RF by using an external resistance. Again, for changing VF, you need a variable DC power supply, which is expensive, and in order to change RF, you need to use extra resistance, which is going to lead to power loss. So each one of them has their disadvantages. Okay, now with this method of speed control, we have a challenge too. And that challenge is the problem or the danger of an open field circuit. So this corresponds to if you have IF equals to 0. How? So we're changing the field current. the speed inversely proportional, the speed varies inversely proportional with the field current, right? Why? Because we said omega is VA over K phi minus RA over K phi square times T. So K phi is a direct function of IF, phi, IF. Okay. So since omega is inversely proportional to K phi, so that is how omega is inversely proportional to the field current as well. So field current, let's say we're decreasing IF, that decreases flux obviously. And what that do is that decreases the value of the E. Remember how E? So E is K phi omega. So you're saying the flux decreases, so that decreases the E. Once that E is decreased, E is decreased, so IA, which is the current flowing through the armature, is given by VA minus E over RA. So once this part, which is subtracted from VA, is decreased, the IA will increase. So that IA will increase. And let's say at one point you have IF equals to 0. That will lead to E equals to 0. Once you have E equals to 0, IA will be one of the highest possible value. So the field current goes to 0. So open circuit of the field circuit, open circuited, leads to phi to nearly 0 value. So why it said nearly 0 value? Because this is the kind of the graph we have for the field and the field current. Right here there is a residual flux, so it does not go to 0. Okay, so phi falls to nearly 0, and IA, as we saw in here, IA leads to a very high value, and the machine will speed up very rapidly, and the armature may fly apart. So IA is the armature current now. Okay, so more the armature current, it's gonna see, okay, it's loaded more, so run more fast. So the DC machine should be available with well-designed protection circuits that open the armature circuit automatically when the field current becomes 0. Now with respect to this field as one of the methods of speed control, we use it under special conditions if we have to bring the speed above the base speed. Okay, if we have to bring the speed above base speed. And that method is called field weakening method. So what happens under field weakening method? Let's say we have a situation when we're saying VA is already applied with its rated value. So whatever maximum VA can be applied, that's been applied. So why I'm saying that? Because you can see that omega is directly proportional to VA. So you can increase the speed by increasing VA. So now VA is at its maximum value. And we are left with, let's say, what we can do with the K phi. So K phi we have to reduce, and how we can do that. When VA reaches to V rated, the further increase in the speed can be done. How? So further increase in the speed is required, but the torque can be reduced. That's the situation under field weakening. So torque is not required to be increased at the same time. So here is the base speed. Okay, so what happens with the field weakening? The armature terminal voltage is at its rated value. As the current IA cannot exceed its rated value now, the speed control beyond the base speed is restricted to the constant power. So VA is there fixed. IA cannot be increased beyond its rated value either, so power needs to remain constant. As power needs to remain constant, so power is constant. So we want to increase the speed, we will lower the torque. Sense? So we will increase the speed and lower the torque. So this is the characteristics here is going to be using field weakening. So special case of change in the field current for the speed control. With the terminal voltage at its maximum value, the speed has to exceed its rated value. This method allows an increase in the speed for the same terminal voltage. An example is in a downhill movement of a vehicle when no more torque is required, but the higher speed is needed. So reducing the K phi or the phi will lead to increase in the speed for the same terminal voltage. That's the field weakening method. Okay, so we are defining here the standstill torque. I did talk a little bit before. Standstill torque is also called the stall torque. So this is the torque at zero speed. Okay, in general, you're gonna see when, and we actually calculated its value, and here it's done again. So S stands for standstill torque, is given by this part in here. And this torque is typically a very high value. As usually, this is small. You saw its values, right? 0.15 ohms, 0.065 ohms, and so on. So this is very small. That's why here in general, we have a large value at zero speed. And with that, what happens is, so now T equals to K phi IA. So if this is large at standstill, we're expecting IASS to be very large. And what will that IASS be? So we're going to say it's only given by, because at standstill there is no EMF induced, so it's going to be only given by the voltage divided by the resistance. In general, IA is VT, let's say, minus E over RA. But at standstill, this is zero. So the current is only limited by the resistance at standstill. So very high current. In order to limit this current temporarily, an external resistance is added in series here. So you increase the total resistance, it's going to lower the current. And again, you increase this, it's going to lower that. So from 0.1 without any resistance to 0.2 with the resistance added. So this is with the resistance RA prime. This is only with the resistance RA. But this is only temporarily done for the startup purposes to limit the amount of the current. And then the external resistance is removed once it leads to a certain speed. Because otherwise, if you will keep the resistance in the circuit, it's going to lead to more power losses and less efficient operation. Okay, so here is an example now. Now let's look through it. Okay, so this example has a trolley bus that's driven by a commutator motor connected through a gearbox of ratio 8 to 1 to the 0.9 meter diameter wheel. So how the system is: first, there is a motor, and whatever it says, the commutator motor, this is, for the time being, you're gonna just assume that it's a DC motor. Okay, and that's the DC motor in here. That's connected through a gearbox. So here is a gearbox. And that gearbox has a ratio of 8 to 1. Soon I'm going to explain what does that mean. And that's connected, so this motor is connected to a wheel in here. So this is a wheel. And the wheel diameter is 0.9 meters. I'm going to say diameter is 0.9 meters. The motor armature is supplied, so this motor is supplied the armature voltage to it. The power supply is supplied by a source of which the voltage can be varied from 0 to 600 volts. So this is the power supply. VA can be 0 to 600 volt. All losses may be ignored, so no armature losses, Now, in order to, the very first thing I want to express in here, so all losses ignored, meaning rotational losses are 0, field winding losses are 0, and armature winding losses are 0. The most important right now to us is having this as 0. Because where is this leading to? IA squared times RA is 0. Now, it is not possible to have this as being 0, only under no load. Otherwise, IA will be non-zero. The other possibility you have is RA being 0. That is possible under all conditions. So, circle it. This is important to us, which we have concluded based on this given statement. Okay. Determine the value of the K phi to give a vehicle the speed of 12.5 meters per second at an armature voltage of 600 volt. So VA is 600 volt, V at the vehicle. Okay, at the vehicle. So here you have the values, and here you will have different values. Now the gearbox, the role of the gearbox, the power remains constant for the gearbox only, I'm saying. That means on its left hand side, on its right hand side, it does not contribute any power, it does not take any power. So power is T times omega. So if you say here is the torque T, here is the speed omega, and let's say here you say the torque is T, the speed is omega prime, sorry, T prime and omega prime, then from this equation P input remains P output, so you're going to have T prime times omega prime equals to T times omega. Okay, so I was saying V is the velocity at the wheel, so we're going to use the primes on left hand side of the gearbox, so those are the motor quantities, and the wheel quantities are without the prime. Okay, so V is without the prime, and that's given by 12.5 meters per second. We know how to convert it to omega. So omega is given by V divided by R, right? V divided by R. You remember the equation, V equals to R times omega. So omega is 12.5. What is the radius of the wheel? The radius of the wheel is 0.9 divided by 2. Okay, and this gives you 27.78 radians per second. Okay, but so far what we have to do, we have to calculate for K phi for that. So in order to calculate for K phi, with respect to the motor, now K phi is related to motor, so that means K phi has to be coming from, if you want to use equation E over omega, it has to be E over omega prime. Okay, so for a motor the equation is VA for a motor, VA E plus IARA. And since RA is 0, so you have VA equals to E. So this is going to be VA over omega prime. VA is known as 600 volt and omega prime is not known, right? VA, we said, see here, these 600 volts. In order to calculate omega prime, what we need to do now? So we need to do something. What is that 8:1 gear ratio mean? So the 8:1 gear ratio mean. Okay, next part of the question we have is with the value of the K phi. So from part 1, is 2.7. Determine the armature current to provide a thrust of 8 kilonewtons. So it's a force given on the trolley bus at the wheel. Okay, so torque will be force times the radius, which is 8 times 0.9 over 2/2 of the diameter, 3.6 kilonewton meters, because it's given in kilo. Okay, so now what we need to calculate, we need to calculate the armature current. So we're going to say T equals to K phi IA. So IA will be, all right, we're in problem again because we are the motor, so it has to be T prime. So T prime we said has to be 1/8. So T prime over K phi, 1/8 of the torque required, 3.6 kilonewton meters over 2.7. So that gives you the current, 166.6, and it's in amperes, not in kiloamperes. Okay, so that's the second part of the question. The third part of the question is we're looking to calculate the speed range above 12.5. So 12.5 it has achieved with 600 volt as the armature voltage. But now we're going to apply field weakening with the constant armature voltage of 600 volts in order to require the speed of 25 meters per second. So now we need V as 25 meters per second. First of all, let's see what is omega. So it's going to be 25 divided by R, which gives you a speed of 55.56 radians per second. And let's bring it to as the motor side, so which is omega prime, so 8 times, and that's gonna give you 444.44 in radians per second. So we are looking, what are we looking for? Constant armature voltage, but we are changing the field. Armature voltage remains constant. So we're gonna have, let's say, E1 equals to K phi 1 omega 1. We're gonna have another equation, E2 K phi 2 omega 2. Now E is same as VA in this case. So in both cases is 600 volts. K phi 1 omega 1, 600 volts equals to K phi 2 omega 2. So that means it's gonna be 1. So dividing the both like this. So 1 equals to, what is K phi 1? K phi 1 is, let's say, we're gonna choose a red color to see the 1 quantities. So here is K phi 1. And the speed corresponding to that was 12.5 meters per second. So that's the speed, first speed, and that has to be, of course, converted to omega prime. And the omega 1, actually, we calculated it in the very first step, in the step number 1. So here we did that. So here was the omega 1, okay, corresponding to 12.5. And the omega 1 was calculated as 222.24. Okay, so I'm going to write in here, this was the value calculated in first part. Although you don't need it really, because you can straight use the velocities as well as it's the ratio of the two quantities. Okay, K phi 2, do we know K phi 2? The answer is, that's what we have to calculate. Do we know omega 2? The answer is yes, we know. So let's use the green pen, and we're gonna say, no, I didn't mean to. Okay, let's do it like this. So 444.44 is your omega 2. So let's substitute everything, and we got it as K 2.7 times 222.24 over K phi 2 multiplied by 444.44. So what are we expecting? Are we expecting a smaller value of K phi 2? The answer is, of course, yes, because speed is inversely proportional to that. If we are increasing the speed, we're expecting a lower value of K phi. And once you complete the calculation, it's 1.35. So that's the new value of K phi 2, which will be used to reduce the field current in order to increase the speed from 12.5 meters per second to 25 meters per second. Gear ratio. So this side is the motor. Here is something in after the motor. Here is the gearbox. And here is the, box. Here is the output of the gearbox, T omega. And I'm gonna say T prime omega prime. Okay, so the gearbox ratio of 8:1 means the torque that motor must exert is 8 times smaller due to the gearbox. So that 8:1 ratio, right? So with that 8:1, it's saying if it has to produce a certain torque, let's say 64 Newton meters at the wheel, then the motor has to produce less torque. How many times less torque? 8 times less torque. The torque that motor must exert is 8 times smaller due to the gearbox. Okay. In order to interpret that, we also know T omega equals to T prime omega prime, and we're looking for omega prime now. So T prime is the motor torque produced. That's going to be 8 times smaller, so only 1/8 of the torque required at the wheel. Torque required at the wheel. Now, if this is true, then we also know that omega prime is going to be 8 times omega from here, right? So that means the omega prime is going to be 8 times, we calculated omega as 27.78, which gives you 222.24 radians per second. And with that, we will be able to K phi, which is 600 volts divided by omega prime, and that gives you 2.7. So that's the first part of the question. Okay, here is another question we're discussing. It's a separately excited motor again that has the following data. So when it says the nameplate data, so these are the rated values. So machine may operate some other number, add some other values. 230 volt is the armature voltage, terminal voltage. V 40 amperes is again the armature current, and that's the speed the machine is running at. Determine the value of the K phi for the operation of this motor under rated conditions. So first one is we're gonna consider those values as it is and we can calculate something. And it's asking us to calculate K phi. So K phi will be from E over omega, but it looks like we need to calculate E first. So E is given by VA minus RAIA over omega. So 230 minus 0.5 times 40 divided by the 1000 RPM converted to radians per second. And the value of the K phi comes to 2. Okay, that's part 1. Part 2, what resistance would be required in series with the armature circuit of this motor to provide a torque of 62.5 Newton meters at a speed of 500 RPM. So in second part it says, we need to have a torque of 62.5, and we need to have a speed of 500 RPM. So it's saying what resistance, let's say we're going to say RA prime as being RA plus R external. So what value of the external resistance needs to be connected in series with the armature resistance, right? So it's doing something like this. So this is VA as 230 volt. This is, it's drawing that current because it's motor. That's, let's say, is the external resistance. This is the resistance as 0.5 RA, and that's your E. So looks like we need to know I first, because IA being 40 amperes was under rated conditions. Now since the speed has changed, the load is different, so we have to see what is IA first. So we're going to use T equals to K phi IA. Now I'm going to say IA is 62.5 divided by K phi, which was calculated as 2, which is okay because we're not changing the field side, okay? So IA is done. E will be K phi omega, which is 2 times the speed. Now it's at 500. So E is 104.72. And then what do I need the resistance? So I'm going to write a KVL in here then. So that KVL will be negative VA plus R external times IA plus RAIA plus E goes to 0. So that's 230 volt equals to R external plus 0.5 times IA, 31.25, plus E is 104.72. So one equation, one unknown, and the R external numerical value comes to 3.5 in ohms. Okay, so that's the second part of the question. So part 3 of the question, what armature voltage would be required to provide a torque of that and the speed of that if no series resistance is added? So here it's looking for the VA value. It's saying no resistance added, but still to have a torque of 62.5 at a speed of 500 RPM. What voltage at the armature needs to be adjusted? So now this circuit looks like this. So that's 0.5 ohms, that's E, and that's VA, which is not 230 volts. Now it's saying adjust that in order to increase the speed, in order to have the speed of 500 RPM to meet a torque of 62.5. So we saw from part 2 that IA calculated as 62.5 over 2 as being K phi gives you a current of this needs to be drawn by the armature. So with that current, now we're looking for the value of VA, and E is also same as part 2, so K phi omega, which is 2 times 500 which gives you 104.72, exact same value. And now I'm gonna say let's apply KVL. So KVL VA equals to E plus RAIA, and we're calculating for VA, so 104.72 plus 0.5 multiplied by 31.25. And that gives you 120.3 volts. So it says we don't need to have 230 volts in there. So that's the value of the VA. So this is the armature voltage control. Part 2 was the armature resistance control. So part 3 is comparing which method is efficient. Sorry, next part 4 is comparing if the part 2 is more efficient or if the part 3 is more efficient, and we're expecting part 3 to be more efficient because that does not involve any resistance. So let's say we're calculating the efficiency for part 2. So P output over P input. And I'm going to come back in here. Here I'm going to say for part 3. So we're solving for part 4 though, but based on part 3. So efficiency, power output is where? Power output, this is a motor, so the rotational losses are not considered in this case because we don't have any ways to consider them. So that's why I'm gonna just consider the developed torque. So I'm gonna say T times omega divided by the input power, which is VA IA. So the torque is 62.5 given to us at a speed of 500 RPM. Divided by VA was calculated 120. IA was 31.25. So in part 3, the efficiency comes to 87%. In part 2, it was the same torque, 62.5, it was the same speed. And the input was, VA was 230 and IA was 31.25. And if you complete the numerical value, it gives you 45.5%. So when we have used the armature resistance control, the efficiency is less. Okay, here is now the shunt DC machine. So this example is particularly for a shunt DC machine. So in case of the shunt DC machine, since it is fed from the same source, the armature winding and the field winding is fed from the same source, so that's why the field current depends on the terminal voltage. So any change in the terminal voltage changes the field current, will change the field current, and that will change K phi, and that will impact the torque speed characteristics. So that's why the terminal voltage is normally kept constant. If the speed control of a DC shunt motor needs to be achieved, it is either achieved by changing the armature resistance, or it's done by changing the K phi, only by changing the RF. All right, so let's look at this example in order to look through some speed control, in order to look through some operation of the DC shunt motor. So a shunt DC machine operates off a 120 volt supply. So that's your VT, which equals to VA, which equals to VF. The machine has the field and the armature resistances of 80 ohms and 0.1 ohms respectively. It draws 51.5 from the supply lines, so that means this is your total current IT. And it spins at 1500 RPM, so that's the speed. Ignoring the rotational losses, good, the rotational losses are 0. Assuming the linearity of the magnetic structure, so that means phi is proportional to IF. So that means we can use the proportionalities. First, we need to calculate the load torque and the efficiency. And since in this case the rotational losses are ignored, so load torque is going to be, it is the output torque is going to be same as the developed torque. Okay, and that's going to use an equation T equals to K phi omega, sorry, K phi IA. So that will be the equation used to calculate the torque. So in that equation, we need the current IA, which is not given in fact, but we have a way to calculate IA because we know this current as being 51.5. We can calculate this current because we know the voltage VF as 120. We know the resistance as being 80. So IF can be calculated as 120 over 80. And once you know that, we can apply KCL, and they're saying IA equals to 51.5 minus 120 over 80. It's in here. So you got that as 50 amperes. So IA can be calculated. In order to calculate K phi, we can use the induced voltage equation, E equals to K phi omega. In order to have E, we can use the armature voltage minus IARA. Armature voltage is 120, IA calculated as 50 in here, and RA is fixed 2.1. So that gives you E. So you know E, you know omega. What is omega? 1500 RPM. So you calculate K phi. Then you use that K phi, and you use the IA as 50, and you calculate the torque as being 36.6. And in order to calculate the efficiency, it's the output over input. So output is the torque times the speed. And the input is the VT, which is 120, multiplied by the total current, 51.5. So has both armature and the field winding. And I believe this number is actually uses the field winding as well, it looks like to me. Or no, let me just have a look. Because you're using input as being 120 and the both the sum of the two currents, so we're okay. Okay, next part of the question. So that's part one, very, very simple. The next part has the speed control. Part two. So the load, torque, efficiency, if an increase in the field resistance to 100 ohms, now field resistance is increased from 80 to 100. If an increase in the field resistance to 100 ohms results in an increase in the speed by 300 RPM. So the speed now is 300 RPM more, which is going to lead it to being 1800 RPM. So the speed is 1800 RPM. Let's see what we're going to do there. So load torque, T equals to K phi IA. This needs to be done, and we're saying F is increased to 100 ohms now, and the speed is increased by 300, which is going to lead to 1800 RPM. And let's say the new values, we're going to use them as 1. Okay, old values, we're going to keep them as it is. All right, so we're changing the field resistance. Now, RF is going to change, IF is going to change K phi, or phi itself, right? Now, it's the increase in RF, which is going to lower the IF, which is going to lower the K phi as well, right? So we're saying we're going to use the new values as 1. So this is going to be 1, this is going to be 1, this is going to be 1. So ultimately where we have to reach K phi IA. So we need a new value of K phi. We need a new value of IA. So how we calculated K phi previously, we calculated E equals to K phi 1 omega 1. This is how we calculated. And we're going to use the same method now for K phi. So we'll have new E1, we'll have new speed, which is already there. In order to have E1, we need K phi 1 actually, okay? And in order to have IA, we need E1, okay? And then I'm going to say IA1 equals to E1, sorry, VVV, my apologies. Eraser. All right. So what I was saying is VA. VA is going to remain constant, right? Because VA is 120 volts. So 120 minus E1 E over RA, which is going to be constant as well, so 0.1. So this is what we're going to be doing. Okay, so in order to reach at K51, we're going to use the proportionality, saying K51 over K5 equals to IF1 over IF equals to RF over RF1. See how they are inversely proportional to the resistance. So new K5, K51, the old K5, you guys remember the value of the K5 from the previous question? It was 0.731. Equals to RF was 80, RF1 is 100. All right, so this gives you a lower value of K51, which is 0.585 as expected. Then I'm going to say E1 is 0.585 times 1800 divided by. So that gives you 110.3 volt. So I'm going to go in here, 120 minus 110.3 divided by 0.1. So IA1 is 97 amperes. So then T is going to be K51 0.585 times 97. And that gives you 56.7 Newton meters. So that's the torque. And what else? We also need to calculate the efficiency. So efficiency will be 56.7 times 1800 converted to radians per second divided by the input voltage, which is 120, multiplied by the total current, which is IF, plus IA. So IA is 97. IF is the voltage. VF now is still 120 divided by the resistance is 100 now, not 80, right? And it gives you an efficiency of 90%. Was the value in the first case? That was 93%. What we did now, we increased the field winding resistance. So the losses are more and the efficiency is less. So that's part 2 of the question. Part 3 of the question, the speed under the same load torque and the parameters as those in part 1. Okay, first of all, what was the load torque in part 1? So we're solving for part 3. The torque was in part 1 calculated as 36.6 Newton meters. And it's also saying what other parameters it's talking about. So it's talking about the RF, IA being the same value. Yeah, okay. And what change is made? The terminal voltage is changed to 150 volt now. And the terminal voltage is actually same as the armature voltage, same as the VF. So this is going to change IF actually. Right? What do we need to calculate? The speed. So in order to reach the speed, let's say we're going to use it as omega prime this time. We're going to say E over K5. And looks like everything will change because we are changing the voltage supply to armature, voltage supply to field. So it's going to change the field current, it's going to change the K5, it's going to change E. Okay, how those changes are implemented now. In order to have E prime, I'm going to say it's the new voltage VT minus IA prime multiplied by the fixed resistance as 0.1, divided by K5 prime. In order to have IA, we're going to use the torque, but since K5 will be different, so let's solve for K5 first. Now, the VF has changed. If VF has changed, IF will change. If IF will change, K5 will change. But this time, if VF is increased, the IF will increase, and that will increase the value of the K5 as well. Let's say we're taking VF prime. So we're going to say VF prime over VF equals to IF prime over IF equals to K phi prime over K phi. So linearity is there. VF prime, the new voltage 150, the old voltage 120. IF prime, 150 divided by 80. Right, guys? Or in fact, we don't need the IF in between. We're going to straight go to K phi. So K phi prime divided by, what was the previous value of the K phi in the first question? 0.731. So that leads to the calculation of a K phi prime. So K phi prime in this case is 0.914. Since we have increased the voltage, increased the current, so the value is high now. So that will be T equals to K phi prime IA prime. So T is 36.3, 0.914 IA prime. So that will lead to IA prime as being equals to 40 amperes. And that being solved, give you the speed. So 150 minus 40 times 0.1 divided by K phi prime, 0.914. And that gives you 159.7 radians per second. And this can be converted to RPM. And once converted to RPM, it gives you 1525 RPM. So from 1500 RPM, it has gone to 1525 RPM. Speed under the same load, torque, and the conditions. Yeah, that's it. So we only need to calculate the speed. Yes. Okay, we're now at the DC series motor. So for a DC machine, these two equations are developed at the very beginning. This is the circuit for the DC series machine. You can see that both the windings, the armature and the field winding, are connected in series, and you can see the current flowing through each winding is same. And that is how the field produced by the field winding depends on the armature current. If we assume a linear relationship between the flux and the current, which is in here, so the actual relationship is like this, right? If we assume the linearity, so that means we're gonna say the graph is actually a straight line. If that is the case, so that means we're gonna say phi is proportional to IF, or we can say phi equals to KF is a constant times IF, okay? And KF there is going to be the slope of the linear part of the graph. If that is the case, in both these equations, we're gonna substitute phi equals to KF times IF. So this is substituted in place of phi. Okay, this is substituted in place of phi as well. So that gives you K times KF. IF is same as, so it's IF times IA. It's IA times IA, as IF is same as IA. So IA square. And here I have replaced the IF with IA as well. Okay, so those are the modified equations for the series motor only. And we're gonna say this constant combined K times KF, we're gonna define it as series motor constant, and we're gonna say KSR. So SR is for the series motor. So the modified equations, or the updated equations for the series DC motor, so torque is KSR IA square. EMF, or the induced voltage in the armature, is KSR IA omega. So from there, torque is proportional to the square of the current. So VT equals to VA plus VF, that's the series motor as well. So VA is substituted as E plus IARA, VF is substituted as RFIF. E got its expression from the previous page, KSR IA omega plus RAIA plus RFIA. So those two can be combined into one, and many a times it's given as one resistance. Okay, and you can have IA common in both equations, so IA can be taken common as well. So from here, IA can be written as a square root of T over KSR ratio. And we substitute that IA in here. So that's from this equation, right? Okay, yeah. And now we're trying to develop an equation of omega as a function of torque again. So that's why we're trying to manipulate the equation. So multiply both sides with root KSR over root T. So the right hand side will be without it and omega will be free. Now divide all the parts of the equation with KSR to have omega without anything and move this factor to the left hand side as well. So we did that, and the omega equals to VT over root T root KSR minus RARF over KSR. And this is not a straight line equation. So it gives you a graph like this. And with that, if you have omega equals to 0, 1, number one, if you have omega equals to 0, it gives you a very, very high value of the standstill torque. And the expression is given by this, by substituting omega equals to 0. Another thing you see that this speed keeps going up and up and up. So that means a series machine cannot be run under light load or no load conditions. So in case of a series motor, the standstill torque is very large. So it could be applied to the applications where the large startup torque is required, like the car engine starters. So at no load, so that is what we're coming in here, closer to these points, so closer to this end. The omega can be infinite, very large speed, so that must be avoided. So a DC series motor should not run at no load. And it is important to have protection devices that remove the electrical power to a series motor when load becomes disconnected. So let's look at a question. Which is on a DC series motor. So it's a DC series motor that has a combined field and armature resistance of 1.2 ohms. When it's connected to a supply of 48 volts at standstill, the motor develops a torque of 1500 Newton meters. Calculate the armature current at the standstill and the series motor constant. So since it is at standstill, omega is 0, so E is also 0. So for the series motor, you have the equation Vt equals to E plus Ia, and the multiplied by the sum of the both the winding resistances. So Vt is 48, E is 0, Ia is unknown, which needs to be calculated. Ra plus Rf both combined is given as 1.2 ohms. So you calculate the current at speed equals to 0 as being 40 amperes. You might realize that's a very large current in comparison to what its running current is going to be. Okay, so keep in mind here it's 40 amperes. The series motor constant we can calculate it as, so we can say T equals to KSR times IA square. So torque is 1500. So torque is 1500. KSR needs to be calculated. This is 40 square. So KSR can be calculated. The series motor constant comes to 0.9375. That's the first part of the equation. Next part of the equation is need to calculate the torque when the machine is running at a speed of 500 RPM. So you might realize how small the current is going to be now. So we're calculating the torque. So now the machine is running at 500 RPM. So speed is 500 RPM. So that's the equation. So you have E plus this. E is KSR omega times IA, and that's completely there. So IA we take common, needs to be calculated. Series motor constant we calculated, 40 is given as constant. So that's the speed 500, that's the combined resistance 1.2. So we calculate the IA being 0.9546. So compare this to 40 amperes. So that was the no load current. So it's more than 40 times. So the torque it will run under that condition is KSR times IA squared. So that's substituted, and that's the value of the torque, the required torque. Part 3 of the question is looking for the efficiency calculation when it's operating at 500 RPM, and we can ignore the rotational losses. So we're given that we can ignore the rotational losses. So the efficiency definition, standard definition, is the ratio of the output power to input power, and this is a series motor. So rotational losses are ignored, so that is how you have P output being equals to P developed, and that can be calculated as T developed times omega. T developed is what we have calculated in here. Let's use this color pen to grab what we need. And since that's the torque developed at the speed 500 RPM, so that will be the speed going from there. So you have T, where is the T? 0.8544, and there's the speed, divided by the input power. So input power in this case is the torque, the supply voltage, multiplied by this is a series motor, so IT, which is the same current as IA. So this is going to be same as VT times IA. So VT is 48 and IA calculated is 0.9546. Right, so that's how you calculate efficiency, and there is a different method to calculate the efficiency is also explained. So if you would like to use that, you can use that as well.